Hi everyone. I wanted to give this try to explain when is a power equal to beta and when is it 1 minus beta. This is a question that has been asked frequently and even in the previous office hours. So I thought that it is worth another try, something extra to what you have in the tutorials and the lecture recording videos. So the answer to that question is never. Power is always 1 minus beta, always. But there are some tricky questions that you might face that might make you think otherwise. Now let's see a couple of examples and different scenarios how this can differ. This question is from assignment 2, part 2, and we have different questions for part 2A and B. The scenario is pretty much the same. We have the amount of time a laboratory worker takes to complete a particular task. The numbers that I have will be different from the numbers that you guys will get in wet work. But I thought that these two examples will be a good indicator of what people might be getting wrong in some scenarios. So the premise of both examples will be the same. The mean of our population will be 209 seconds and with a standard deviation of 22 and a sample size of 20. So what is our X bar here? The question is asking that consider using a significance level of 5%. So our alpha will be 0.05. It's only a one-sided alpha. It's asking to detect only a reduction. So our Z would be minus 1.65. You can use negative 1.64 as well. No difference here. It's just different numbers. Our null hypothesis here in this example, in this scenario, will be that our mu is 209. Our alternative is that mu is less than 209. This is basically what we've always been looking at. We have the familiar bell curve. We have our mu. We have our X bar. And anything below this would be our rejection region. And anything above our critical value, we fail to reject the null hypothesis. You are very familiar with this. Up until now, you've faced a lot of examples for this here. So we'll basically just skip through the calculations. These are here if you needed to check the numbers. But basically the main important point here is that when we solve for x, we will get to 200.88 seconds. So our critical value for alpha of 0.05 or a z of 1.65. Here it's negative because we are looking at a reduction. Our value is 200.88 seconds. So any estimate below this value, anything below this X bar is considered in our rejection region, and anything above it will fail to reject the null hypothesis. Now remember this because we are going to use this part in the main examples. Just a quick reminder, what is type 1 error or alpha? It's basically rejecting the null hypothesis when in reality our null is true. So in this example, if the true mean of the population is 209 seconds, meaning that even if the amount of time a laboratory worker takes to complete that task is 209 seconds in reality, that's true mean of the population. With the critical value of 200.88 seconds, 5% of the time we will have a sample mean of 200.88 and below, even though this is the true mean of the population. Now, the real example starts here. Power calculations. So the question is asking that in order to detect a decrease of 17 seconds, then what is our power with the scenario that we went through? So what is this question actually asking? So to detect a decrease of 17 seconds, it means that imagine instead of 209 seconds being the true mean of the population, it is actually 192. 192 seconds is the actual mean of the population. That's our alternative hypothesis here. We had this black curve. We looked at all the numbers. We know our x bar is 200.88 seconds. Anything below that, we reject the null hypothesis. Anything above that, we fail to reject the null hypothesis. Now, in the second part, when we are calculating a power, we are not just talking about our null hypothesis, we are talking about an alternative hypothesis. How do we do that power calculation? We calculate the Z beta, and then we estimate the area under the curve for beta, and then 1 minus that area, 1 minus beta is power. This is our framework for calculating power. Now, let's do a reminder of what is our type 2 error or beta. Type 2 error has to be failing to reject the null hypothesis, when in reality, our null is false. So the null is false, but we fail to reject it. Instead of the null is false, we can also say our alternative is true. So in the context of our example, imagine the true mean of the population is not 209 seconds. Our null hypothesis is false. Instead, the true mean of the population is 192 seconds, or 17 seconds less. That's what our question was asking. This is the difference we wish to detect. So our alternative here is true. It's like, imagine instead of our null being true, our null is false, and our alternative is the true mean of the population. So 192 is the true mean of the population now. Remember, we said that any estimate below our initial critical value, or our x bar, which was 200.88 seconds, is considered in the rejection region, and anything above it will fail to reject the. Now that we have solved x, we would put that value in the context of z beta and that formula. So you can go over the calculations, but our z beta would be 1.81, and that's a positive value. Now here comes the tricky part. Now this is the z that we have. Now how can I know if I have to calculate it like 1 minus beta or beta? It's not that. That is not the question that you should be asking. You should be asking that, so this is our x bar here, or 200.88. Anything below this, we reject the null, and anything above it, we fail to reject the null. What was beta or type 2 error? It was we fail to reject the null, so x is above this critical value point, but when our h null is false and our alternative hypothesis is true. So we are working with this critical value and anything above that and the red curve for beta. So this shade of red is the area under the curve for beta or type 2 error, which was failing to reject the null when our alternative hypothesis is true. So here in this example, we have a z-score of plus 181. The area under the curve in the tail would be 0.035. That's what we use the z-table for. And then we understood that area is beta in this example, according to the figure that we just saw. So we know that beta is 0.035 and power is 1 minus beta always, and this 0.965 is our power in this example. So let's go to another example. Again, same question, same assignment, but instead we're going to check part 2b. It has the same premise. It's the amount of time a laboratory worker takes to complete a particular task. Our mean or mu naught is 209 seconds, standard deviation 22, sample size of 20. Same thing. We can solve for x bar. Again, the situation is the same. Our null hypothesis, our alternative, significance level we are using is the same. So our z alpha will be again negative 1.65. So basically up until now, everything is the same. The critical value is still 200.88 seconds for an alpha of 0.05. So any estimate below this value is considered in the rejection region, and anything above it will fail to reject the null. Everything the same up until now. But now, this example is different in the sense that the difference we wish to detect is lower. So instead of 17 seconds, here we want to detect a decrease of 7 seconds. So it's basically like our true population mean is 202 seconds. What do we, the question is asking to calculate the power. So again, let's think what the question really is asking. So to detect a decrease of 7 seconds, it means that, imagine, instead of 209 seconds being the true mean of the population, 202 is the actual mean of the population. Again, same black curve, same X bar, same rejection region here, same anything below this X, we reject the null. Anything above this X, we fail to reject the null. But now we are working with an alternative hypothesis, which is the red curve. Again, how do we calculate power? We calculate the z beta and then the area under the curve for beta, and then 1 minus beta is power. What was type 2 error or beta? It was failing to reject the null when in reality null is false or alternative is true. In the context of this example, imagine the true mean of the population is not 209 seconds. So our H null is false. Instead, the true mean of the population is 202 seconds, or as the question is asking, 7 seconds less. So our alternative hypothesis is true. Or it's like we are imagining our alternative is true. Now remember, again, in our example, any estimate below the initial critical value or 200.88 seconds is considered in the rejection region, and anything above it will fail to reject the null. So in order to fail to reject the null, X has to be above this value. So now we know that X has to be above this value in order to fail to reject the null, and instead of working with the black curve, we are working with the red curve, because we are imagining that instead of the true mean of the population being 209 seconds, in this scenario it's 202 seconds. So this shade of red, this area is our beta, because it's X above this value, so it's in the fail to reject region, and we are working with the area under the curve of the red curve. So this is our beta. Now, when we have this X and we get the z-score for this value, the thing is, the z-table that we use does not have the negative value of the z's, it only has the positive values of the z's. But what we do is that we mirror this and calculate the mirror of this area on the positive side. We just imagine it's on the negative side. So when we use the z-table for getting a z-score here for the beta, for the alternative, and then get the area under the curve, it will show us this region. And the red shade is our beta, and the non-shaded area under the curve, under the red curve, is our 1 minus beta. Now we solve for z beta. We get a z beta of minus 0.23. When we look at our z table, z of minus 1023, the area under the curve in the lower tail would be 0.409. Basically, we are looking at the upper tail. It's just the negative means it's on the lower tail, not on the upper tail. And we understood that that area, that non-shaded area, is 1 minus beta, and the shaded area was beta. So basically this number is our power here. It's 1 minus beta is equal to this number. And our beta, the red shade under the red curve, was 0.591. This is our type 2 error, and this is our power in this example. I tried my very best to give you numbers and figures in order to know that just in the end, why do we sometimes do, like, we get a z-score here and then get the area under the curve and do a 1 minus this area under the curve, or sometimes we don't do the 1 minus area under the curve. I hope that this helped you guys understand, and in future examples you might be able to come back to this example and just review everything again for any sort of exams. And hope this helped, and best of luck.